Hey everyone! We're back in the shader editor again, and this time I'm bringing you a tutorial on how to create parallax effects. Parallax can be useful to create fake depth on flat surfaces, where you might not want to use a volume shader or add extra geometry. In this video, we'll take a look on how we can create a parallax offset node like this, which allows us to shift a texture into a face. This works on any kind of shape, like this cube for example, and it correctly shifts into the face every time. This video is the first part of a two-part tutorial series, where we'll be looking at the basic concept of parallax, whereas in the second video we'll take a look at how to create fake rooms complete with walls and different layers. So let's get started. A very simple way to do a parallax effect is using the texture coordinate node, and we have a reflection output right here, which we can plug straight into the texture, and it's going to give us already kind of view-based offset. This is because the reflection vector takes the vector from the view to the surface, and then outputs the same vector but reflected along the surface normal. So essentially as if we were shining light at the surface and it reflects off. So if I change the angle of this view, if we have a more shallow angle and look from the side, we get a more drastic effect. While if we look at a very steep angle and look down, we can see it's more flat. Of course this changes based on how the surface rotates and everything. So this is excellent for a view-based effect. And if we take our object coordinates and mix them with the reflection coordinates, we can see that we can get more control over how strong our offset is. So this would be the unshifted object coordinates, and now we mix it with a reflection, and it's going to shift the texture downwards. But as you can see, it creates this warping effect the further we go out. If you don't mind it, that might be perfect for you to get a very easy and quick parallax effect. But what we're going to do instead is take our input UV map and apply shift to it. We can do this with a vector math add, and usually we input single values, so we can just shift the texture how we want. But in this case, we're going to calculate those values to correctly apply the fake offset. And the way we do this is by taking a geometry node, which has an incoming output. And incoming gives us the vector from the surface to the camera. And if we scale that by -1, we get the vector from a camera to the surface. If we visualize this, this would be as if we only take the red vector here, so from the camera to the surface from our view, and we don't get this reflected vector, so we can use it with more versatility. And if we plug this into a texture, we can see this gives us a view-based offset. But the problem with it is that this only works on flat surfaces. On a cube, for example, we get completely different results on every face. This is because this vector has no understanding of what our faces, where our faces are, and which direction they're facing. So this is the goal. We're trying to convert this vector into the local coordinate system of each face. So if you take a look at our coordinates right now, this is just our object coordinates. The z goes up, the y goes in this direction, x in this direction, because this vector is in world space, so it's like a global coordinate system here. So we need to interpret our vector on the faces, which is called the tangent space. So if we take a look at this, this is how we want to orient our vector depending on which face we're looking at. And we can create a function like this, which converts a vector from world space to tangent space. So first we need to take our geometry normal, which is going to be our up direction. So it's going to be blue because the z component is 1 and the rest is 0. We also need a tangent node. Switch to UV map because we need the UV tangent. And this is going to be our x-axis, so a 1, 0, 0 vector. And now we can calculate the bitangent from this, which is going to be our y-axis by taking the cross product. And for safety we normalize this, even though the output should be normalized, but in case we have custom normal data or custom tangents, whatever, we want to make sure that our bitangent or y-axis is going to be always normalized. So we have our three vectors which determine our space. And if we want to interpret our vector in this coordinate space, we take the dot product with each vector separately, like this. So normal to here, bitangent to here, there we go. So this is with our x-axis, this is with our y-axis, this is with our z-axis. And we can combine these back into one vector. And suddenly we get coordinates which look the same from every side. So if we add this to our UV map, we see it doesn't change anything for the plane. But if we take a look at the cube, it's going to correctly project on every side. So this solves the problem by converting it to tangent space. We can group that up and call it world to tangent. But if we take a look on the other side of the cube, we see those three faces are completely messed up. This is because, looking at a UV map, those faces have a tangent that goes from left to right, whereas on the other faces, on the three that are problematic, it goes from right to left. Because if we compute our cross product right here, this is going to flip our bitangent downwards for the cases where our tangent goes from right to left. So we need to flip the bitangent based on which direction our tangent is going. And we flip using the tangent sign attribute. This gives us a value either 1 or -1 based on which direction our tangent is going. So on these faces where tangent goes from left to right, our sign is 1, and on the other faces where it goes from right to left, we have -1. And we can just scale our bitangent by this value, and this is going to flip it so we always have an upwards facing bitangent no matter which direction our tangent is going. So if you take a look outside, we can see that on every face of our cube the projection is now correct, and we get the same coordinate system for every single face. And now we can group that up. This is our input coordinates, this is a scaled vector, and now we're going to add a depth input, which is going to give us control on how strong our offset is. So if we just take this and scale our vector by it, we can control the depth this way. So a depth of 0 gives no offset, and the further we increase, the further it shifts down. But now we will notice the distortion if our angle gets very, very shallow. So we need to somehow calculate the viewing angle to correct for that. And we can just get the viewing angle by taking the z output of our world to tangent function. Scale it by -1. And now the more shallow our angle becomes, the darker the distant points get. And if you look from above, it's going to be completely white. And we now take our depth and divide it by the value. And now this is going to correctly account for our perspective. So it now has a flat projection downwards and gives a correct look no matter where we're viewing from. So let's name this group PARALLAX offset, which already does what we need. But because we're shifting against the normal on our backface, this is going to look messed up. Of course, this would be the correct look because it's being shifted into a perspective from here and away from a perspective from here. But if you want the effect to instead go into the face, no matter which side we're viewing from, we can correct that as well by going into our world to tangent node. And we will simply invert the bitangent, or the dot product from the bitangent, by taking a mix multiply node and the geometry backfacing output. And based on our backfacing, we'll take a value -1 and multiply it by it. So if it's a backface, we multiply this value by -1. So we essentially mirror our space on the backside, so it gives the exact same result, no matter which side we're viewing from. Of course, this also works on the cube again. We take a look inside. As you can see, we always shift away, so this works as intended. However, there's a slight difference for procedural textures. If we take a Voronoi texture, for example, this is going to look the same for now, but if we change our depth, it's going to change the look of our texture. Because in here, we still consider the z component of our view vector. So that means we get the slice of our 3D space at the depth we're setting here. So instead of simply, like on a pixel texture, shifting downwards because it has no z component, instead we say, okay, apply the shift, but we also take the z, and therefore we get a change because our Voronoi texture is 3-dimensional. If we take a 2D texture, this works because there's no z component. But if you want to keep your 3D texture, this might not be the solution for you. So instead in here we multiply by 110. This simply flattens our Z, and this way we always get a flag projection, no matter if you're using a procedural texture or not. However, we can add a little switch for that. We take a new input, add a boolean, let's see, boolean, call it slice, combine x, y, z, x and y are going to be 1 because we don't want to change these, and we multiply this slice value instead. So if we enable slice now, this is going to be considered 1, and so we take the z-axis into account. If we disable slice, z is going to be 0. So if it's off, it's not going to shift through 3D space, but if we enable slice, we can see it changes based on the depth. Of course, this doesn't change anything for our grid, because it has no z component, so it always looks the same no matter if we have slice enabled or not. We can optimize this node a little. This is because we scale our whole incoming vector by -1, and then we later invert the z-axis again, and that's kind of pointless. Instead we can just take the incoming by itself, remove the inversion here, and then simply set the x and y to -1 for the slice. So instead of negating everything, then negating the z again, we simply keep it the way it is and just negate the x and y. So we save a few nodes on that. So this is a working PARALLAX offset node, which works on pixel textures and procedural textures alike, where we can choose if we want to consider the z component or not. And it's going to work on every kind of shape and always get the right coordinates, no matter what object. So if we take a sphere, for example, this is also going to work and shift into the face. Now you can use this node group multiple times to create different layers of effects without ever needing to use a volume shader. So thanks everyone for watching. I hope you enjoyed this tutorial. The finished node group will be available on my Gumroad page for free. If you enjoy my content, please leave a like on the video, it helps me out a lot. Thank you very much, and I'll see you in the next episode. Bye bye!